All right, in this lesson, we're going to talk about something called accuracy, precision, and significant figures. Now, you may have seen some of this stuff before. Certainly, accuracy and precision are common topics. Accuracy is a measure of how close a measurement comes to the true value of whatever is measured. So if you are measuring, say, your weight on a scale, and you stand on the scale and it says 124.6, okay? If you know that you weigh about 125, you're probably going to think, yeah, that's great. It's right on the money. Perfect. That would be an accurate measurement. However, if you get on the scale, instead of saying 124.6, you get on and it says 205. Well, if you know that you weigh pretty close to 125, you might think something is wrong with the accuracy of your balance. So you might get off and get on again, and this time it says 207. You're like, wait a minute, something is very wrong with this balance, this scale. So you get on again and it says 203. All right, well, that would be an example of something that is not accurate, but it is precise. In other words, all your measurements are very close to one another. They may not be accurate, but they are precise. That's the difference in the two terms. To evaluate accuracy, the measured value has to be compared to whatever the accepted value is. Well, you know you weigh 125, that would be the accepted value. Precision, on the other hand, you compare a bunch of measurements to each other. And if they're close, then that would be precise. Often people use bullseyes to demonstrate accuracy and precision. So if the goal is to hit it in the bullseye, the dead center, this would be good accuracy. It's going right into the center, as well as good precision because they're all in the same location. Over here, they didn't get any in the desired location, and they're all over the place. So this would be poor precision and poor accuracy. This one is a good example of precision is pretty good, but the accuracy is pretty low because you want them to be in the center. Okay, this one I'm not going to really talk about. All right, so when it comes to making measurements, and you guys will be making lots of measurements in chemistry class, a measurement always has some degree of uncertainty associated with it. Every time you make the measurement, even if you get it off of a digital balance or a digital thermometer, it always has some degree of uncertainty. How uncertain the measurement is depends on the quality of the device. Okay? If you have a very good balance, you can get to that kind of accuracy. Okay, very close to 1/10,000th of a gram. And the person making the measurement, because you're not going to be familiar with all of the equipment we're using in this class. The last number you make in any measurement is an estimate, even on a digital balance. The other numbers are certain. So if I have two measurements here, and I get on the scale and it says I weigh 130 pounds, that 0 is an estimate, even if it's digital. This one where it says 133.6, that is my estimate. And the difference between them is the quality of the device you're using. Okay, this kind of a scale is going to be more expensive than that one. Okay, now if you're measuring with a ruler, you want to measure all the digits you know for sure and at least one uncertain digit. So if you look at this, I'm going to say, all right, that's at least 3. And looks to me like it might be a little above that line. 1, 2, 3, 4, 3.4, maybe 3.41 centimeters. So I know, based on my picture, that it's at least 3.4 centimeters. Might be a little more, might be a little less. This is an estimate. So some other possible answers you could get would be those. So one more, I think. Doesn't mean that these are wrong and this one is right. What it means is there is certain numbers that you are absolutely dead certain about. This one is an estimate. The easiest way to figure it out is to look at the smallest increment, 0.1 centimeters, divide by 2, and make sure you put a number in that place, that decimal place. So I have to have something in the 100ths position. So all the digits except the last are called certain numbers. The last one is estimated, so it's called an uncertain number. When you make a measurement, you should record all the numbers you know for sure, plus the first uncertain number. doing a graduated cylinder, you're going to be using these a lot. There is this little curve right here that is called a meniscus, and you always read from the bottom of the meniscus. So if this is the 30 mark and that's the 40 mark, there's my 35. Right here is going to be 36. So I know it's at least 36 milliliters, and I know it's not 37. It's somewhere in that range. So these are my certain numbers, 36 point maybe 5 milliliters. So with this one, you could also say 36.6 maybe, 36.7, 36 point maybe 4, 46.8. It's not that they're wrong. This is an estimate, and this is all about the person making the measurement. And the way you can tell, again, take the smallest increment, in this case 1 milliliter, divide by 2, not 0.05, 0.5 milliliters. You need to have a number in that position. It doesn't have to be a 5. It could be, an 8 or a 0 even, but you need to make sure you have a number in the tenths position. So sig figs, or significant figures, are numbers that are recorded in a measurement, all of the certain ones plus one uncertain one. The more sig figs you have, the more accurate your measurement is, and it makes your calculations you do with the sig figs better. So you want to get as many sig figs as possible. So when you're making a measurement, the easiest way to determine how many sig figs you should record is figure out the smallest increment and divide it in half. And it should have a number in that decimal place, even if it is a 0. So if you think it's right on the line, that meniscus is right on the line, you would say 36.0, because the smallest increment was 1 milliliter divided by 2, means you need to have a number in the tenths position. All right, when you're using sig figs and in calculations, this is where you have to carry through what you know about making the measurements into the calculations. And so you have to identify how many sig figs there are. So there are some rules. First of all non-zero digits are significant. That means numbers 1 through 9 are significant. If you have a 0 that is a placeholder, it is never a sig fig. Now there's two different kinds of placeholders. Either you have leading zeros that are in front of, to the left of all the non-zero digits. So for example, 0.005. Or trailing zeros without a decimal point, 500. Okay, these are leading zeros. These are trailing zeros. This is 5 over 1,000. That's why it's considered to be non-significant, because all it is telling you the magnitude of that 5. Well, the same thing here. This is 5 times 100. Again, it's a magnitude. It doesn't tell you anything about the sig figs, though. The other kind of zeros you have to deal with are sandwich zeros. That's anytime you have them in between non-zero digits. They count as significant. Oops, let me go back for that. So if I had 101, there are 3 sig figs in that question. If I had 1000001, all of those numbers are sig figs. What that tells you is that somebody actually sat down and measured whatever it is and said, oh my God, look at that. It is 10,000,001 gram. I mean, how weird is that? But whatever it is, that's how they come up with these numbers. If it is a sandwich zero, it counts. Now the trailing zeros, the ones to the right of a number, are significant if the number is written with a decimal point. Now, I realize that if you know the number 500, you know there's a decimal point there. But if you don't see it written in, this is the convention that they have come up with. If you don't see it written in, then if it's not there, it has 1 sig fig. If it's there, all of a sudden it has 3 sig figs, because it tells you that somebody sat down and went out and measured something and said, oh my gosh, look at that. It is exactly 500 feet, or whatever it is. Not 501, not 499, 500. It's telling you by putting that decimal there that those numbers count. So trailing zeros are to the right of a non-zero number. That's these guys. And they count if you see a decimal point written. I know you know it's there, but if you see it, it counts. So With regards to scientific notation, if you have a number in scientific notation, 1.30 e to the third, the multiplier part, the number in front of the power of 10, is sig figs. Always. All of it is sig figs because there's a decimal. E to the third does not count for sig figs, so that would have 3 sig figs. And then if you have exact numbers or a conversion factor, like a counting number, okay, there is no uncertainty associated with that. If I'm counting 31 students in the room, it's not like, oh yeah, maybe there's 29 and a half or 31 and a half. No, there are 31 students. I am counting them. And then conversions, if you have English or metric conversions, 12 inches, 1 foot is unlimited sig figs. So a lot of times we write infinite sig figs. Same thing, infinite for this one. So I'm going to go through, and each one of these I'm going to identify how many sig figs they have. So for the first one, those 3 non-zero digits count. This 0 is a trailing 0, and there's a decimal point, so I see 4 sig figs. In this, I see a 1 non-zero number, I see a bunch of trailing zeros, and I see a decimal, so it has 3 sig figs. These zeros to the left of the 3 do not count for sig figs because they are leading zeros. Scientific notation, only the multiplier counts, 3 sig figs. This one, I see 1, and these zeros are all trailing zeros, but I don't see a decimal, so I'm going to call it 1 sig fig. In here, I have non-zero numbers, I have sandwiched zeros, and I have a trailing 0 with a decimal point, so all of them count, 6 sig figs. In this one, non-zero number, a bunch of leading zeros do not count, 1 sig fig. And 25 pencils, that tells you you're counting something. There's no discrepancy, infinite sig figs. Now, where this comes into play is when you're doing calculations with sig figs. Anytime you have an uncertainty in a measurement, you have to carry it through when you're doing calculations with that measurement. So if you're calculating area and you're taking length times width, well, you need to make sure that the uncertainty associated with measuring the length and measuring the width is carried through in calculating the area. So there are rules, and you need to pay attention to them. We are going to do them all year. Multiplication and division, the rule is number of sig figs in the answer, final answer, is based on the numbers with the smallest number of sig figs in the problem. Whatever the calculator says, you're going to have to round to the correct number of sig figs. So if I do this calculation on my calculator says 6.384. Well, this has 3 sig figs, that has 2. That means my answer cannot be 6.384. It has to only have 2 sig figs. The 8 rounds up the 3. 6.4 is my answer. I'll do this calculation. And my calculator says 0.145631068. Wow, lots of numbers. Calculators do that. But based on sig fig rules, this has 4. This has 3. That is a trailing 0 with a decimal. That means my answer can only have 3 sig figs. The 6 rounds up to 5. I get that for an answer. Okay, now I'm going to show you these guys. So 975 times 4 is 3,900. That is what it says on the calculator. However, if we're following sig fig rules, that has 3, this has 1. My answer is only allowed to have 1 sig fig. So that is what I have to write. Even though 3,900 is a little different, there's some uncertainty associated with that 4. I have to keep it 4,000. Now with this one, I have 3 sig figs and I have 2 sig figs. My answer has to have 2. Perfect. It works out great. Now, if I put that decimal in there, all of a sudden I have 4. So I want to make sure that I don't put the decimal in there. And then with the last one, it's probably the trickiest one of the bunch, and it doesn't happen very often. 3 sig figs, 3 sig figs. The answer is still 3,900, but you cannot turn 3,900 into 3 sig figs by, say, putting a decimal here. Well, that makes it 390, and it actually has 4 sig figs. So if I do that, well, it has 3 sig figs, but 390 and 3,900 are different by a factor of 10. So you cannot do this as a standard number. It has to be in scientific notation to get the correct number of sig figs. It doesn't happen very often, but when it does, you have to watch out for that. Adding and subtracting, the way it works is you round the answer to the smallest number of decimal places. In other words, the answer has the same number of sig figs past the decimal point as the number in the problem with the least number of sig figs past the decimal point. All you are worried about is what is past the decimal point. You are not worried about what is to the left or leading to the decimal point. So if I do this calculation, my calculator says 31.123. Well, this has 2 sig figs after the decimal point, 1 and 3. I'm not worried about these numbers in front, only worried about after the decimal point. So I have to round it to 1 sig fig. The 2 does not round it up. That's why my answer is 31.1. If I do this, you get 145.78. And again, 1 after the decimal point, 2 after the decimal point means only 1. 8 rounds up to 7. Now this next one's a little tricky because clearly 214 minus 0.15 is not 214. However, this has 0 sig figs after the decimal point. This has 2. That means my answer has 0 after the decimal point. So 213.85, the 8 rounds up to 3. 214 is the answer. So now what I want you to do is pause the movie, and we're going to practice these calculations and doing them to the correct number of sig figs and practicing how to do some of them like this one on your calculator. All right, so for the first one, my calculator says 5.21664. This has 3 sig figs. That has 4 sig figs. That means I only want 3. The 6 rounds up the 1. 5.22. That is the correct answer. 21 divided by 8. Calculator says 2.625. This has 2 sig figs. This has only 1. That means I only have 1. I have to round that 2 up. My correct answer is 3 with only 1 sig fig. The next one, my calculator says 0.013764. And this particular problem illustrates a very good practice for you. This one has 2 sig figs, 3, only 1. That means I can only have 1 sig fig. Recognize that those zeros are leading zeros. They don't count regardless. You have to include them, but they do not count. So I'm only looking at the 1. The 3 does not round it up, so my correct answer is 0.01. Or you can put it in scientific notation, 1e negative 2, and always have the correct number of sig figs. That's the advantage of scientific notation. All right, 10 divided by 2, everybody knows that is 5. However, this has 4 sig figs, so does this one. It needs to have 4. Now, if I do that, I change the answer from 5 to 5,000. But if I put that decimal in there, it's still 5. And it has 4 sig figs. So you might occasionally have to add trailing zeros. Leading zeros you have to include, but they don't count for sig figs. Okay, for this particular problem, please remember how to type things into your graphing calculator correctly using scientific notation. My calculator says 3.666. 2 sig figs, 2 sig figs, only have 2, 6 rounds up to 6, you get 3.7. Now these are addition and subtraction. They're done differently. You won't do them very often. Primarily you'll do them in lab situations, but you will have to do them. So if I add those numbers together, my calculator says 119.45. And then I'm going to count the sig figs just past the decimal point, not in front to the left of the decimal point. 1, 2, and 1. That means I can only have one number after the decimal point, so 119.5. This part to the left of the decimal point does not count for sig figs, only past the decimal point if you're doing addition or subtraction. And then this last problem actually illustrates primarily what you'll be doing in the lab. You're going to have two sig figs after the decimal point. So when you subtract 121.46, two sig figs, you're done. Don't worry about the ones to the left of the decimal point, only the ones to the right.